This is the greatest force ever applied to move a vehicle. This is the cluster of rocket engines boosting the Saturn vehicle free of gravity, straight up. Saturn is the largest rocket ever produced by the United States. Not a military rocket, Saturn was designed solely as a space vehicle. It can carry multi-ton payloads into Earth orbit or to the moon. And the scientific space exploration by Saturn rockets will lead eventually to placing a man on the moon and returning him safely to Earth. But all the missions planned for Saturn hinge on one essential element of space rocketry. If we fill a sphere with highly pressurized gases, there can be no action and reaction. The pressures are equal in all directions, and the gas remains motionless. But if a hole is cut in the sphere, the pressurized gas rushes to escape. Thus we have an imbalance of pressure in the sphere in these two directions. Similarly, if we fill a balloon with compressed air, there is a greater pressure within the balloon than outside. When we release the air within the balloon, the column of air escaping sets up a momentum going in one direction, and the reaction in the other direction, acting as pressure on the interior of the balloon, propels our little rocket. If we look at a representation of a rocket engine's thrust chamber, we see the same principle applied. Through combustion in the thrust chamber, great amounts of energy are released. Hot, expanding gas escapes through the nozzle throat. Because of the design of the nozzle, the mass of escaping gas molecules is accelerated rapidly. This kinetic energy, bursting from the nozzle exit at supersonic speed, generates an enormous force. From the mass and acceleration of the gas flow is computed a basic measurement of rocket power, thrust. The reaction to this thrust is expressed in pressure against the top of the chamber here, against the sides here, and against the interior walls of the nozzle here, forcing the thrust chamber, and with it, the entire body of the rocket upward. Oh, and one other thing. Many people in the past thought that the rocket required a solid body of atmosphere to push against in order to move. Incorrect.
My little balloon lip. Okay, so essentially pro-moon landers and people at NASA as well, they all tend to think that the action of the air rushing out at high speed, okay, in this direction will give you an equal and opposite reaction in this direction, which acts upon the inner wall of the balloon and thus propels it forward. Obviously, you know, when we let go of a balloon, it just pops out and flies everywhere. But that's their explanation as to how it works. Okay, now if we take a look at a rocket engine, okay, a rocket, what we'd see is that here's my little rocket. Okie dokie, dum dum dum. There's my nozzle. Pretty good, eh? Now we've got the fuel and oxidizer tanks. We've got pipes which lead down to pumps and turbines and things, which basically pump the fuel and the oxidizer into the combustion chamber, where the they use hypergolic fuels, so they ignite upon contact with oxygen, and they cause a rapid expansion of gases, and then they expand out at very, very high speed to create thrust, or a thrust force, which then gets chocked out in the back of the nozzle. Okay, now pro-moon landers and lots of people at NASA tend to think, or tend to promote the idea, that merely the action of the exhaust coming out from the combustion here to here will create an opposite and equal reaction that forces, or that causes, the rocket to move, to be propelled forward. Okay, so basically all of these, the fuel and the liquid, the molecules moving in one direction here, cause an equal and opposite reaction actually on the base of the rocket, which pushes it forward. Now that's their idea on how a rocket works. One very important thing to mention, and that is, as soon as all these gases here leave the nozzle, they are no longer effective in the forward propulsion of the rocket. That's what pro-moon landers and people at NASA say. Okay, so that's something to bear in mind. Okay, now here's my explanation as to how a rocket works. Okay, so here we go again. There we go. We've got our little big wide nozzle there. There we go. We've got our fuel tanks and oxidizer tanks. We've got the pipe work, goes down to turbines. Now, so the fuel and the oxidizer get pumped into the thrust chamber, or into the combustion chamber, very high speed. You get a burn or combustion of the gases. They expand and they are forced out through the nozzle at extremely high speeds. Obviously, when we watch a rocket lift off and launch, we see this. You know, it's clearly observable. Now, what I think happens is that the action of this thrust force here causes a reaction by the mass that is behind the rocket. So if I just turn this around for everyone to see. So the rocket, the thrust force coming out the nozzle hits the mass, and the mass gives an opposite and equal reaction that acts on the contact area here that pushes the rocket in this direction. One very important thing that a lot of people tend to overlook, and that is a rocket is one mass system. So all of this, all of that there should be regarded as one mass system. You've got fuel, you've got thrust, and you've got the actual mass of the rocket itself. All that is one mass system, and that solely acts on the mass, whether it be the Earth, whether it be atmosphere, that gives you an equal and opposite reaction. So that's my understanding of how a rocket works. Okay, now we're going to put this to the test. So what we're going to do now is we're going to use our little balloon car as our little experiment to see who's right and who is wrong. There we go, and see how well it performs. See what it does. There we go. So we've blown up our balloon, and there we go. There we go. And as you can see, there we go. It's going pretty well. What I'm saying basically is that the air just coming out of the straw acts on the atmosphere that's in the room, which causes a reaction which then pushes the whole lot forward. Because you've got to remember, and that is that the air coming out of the straw actually moves with the vehicle. It doesn't get left behind or anything, it actually moves with it. That's why we have to remember that it's a mass system. Okay, so how we're going to check to see whether who's right or who's wrong is what we're going to do. We're going to divert the air that comes out of the straw.
On landing, however, deceleration is wanted, and then thrust reversers are used. These are flaps that move to divert the gas forwards rather than backwards through the exhaust. This has the effect of slowing the aircraft down.
We can do this simply by using a piece of paper. We're going to attach. There we go. Now I'm going to put the paper. I hope everyone can see this. There's at least a 2-inch gap there. I'm not sure whether everyone can see that. There we go. There's a gap where the straw, from the distance from the end of the straw to the paper. Basically, you're not restricting the air movement that's coming out of the bottle and the straw, so because the air can dissipate everywhere out the sides and everything. Okay, now if Pro Moon landers are correct in that the air moving this direction will cause an equal and opposite direction force in that direction, then it should move. Whereas if I'm correct and that it needs the mass of the atmosphere to act against, this shouldn't move, basically. Okay, because we've actually diverted the thrust force of the balloon car. Okay, so we're going to now put it to the test. So here we go. Let's just line it up. Here we go, and we're off. And we're off. And we're off. It's not moving. What we're going to do? It's not working at all, and it's not moving. The balloon's going down, the air's coming out the straw, it's hitting the straw, I can feel the air from the side, and it hasn't moved one little bit. There we go. If we go back to how a rocket works in space, we have to remember that in space there is a vacuum where basically matter is very, very, very sparsely populated in a given area. Okay, so you got fuel tanks, and my pen's running out. There we go. So what's going to happen is that we're going to have the fuel, or what could happen, I should say, is let me just change my pen. There we go. We've got a nice purpley one here. There we go. There we go. That's better. What's going to happen in a vacuum when the rocket's in space? And that is the fuel is going to be pumped out. Okay, you're going to have combustion, you're going to have the thrust force coming out, okay, out of there, but there is no mass there for it to act upon. Therefore, you won't get the reaction in this direction. You will not get that because there is no mass for this thrust force to act upon. Now we've clearly demonstrated that with the balloon car in the video, but also one of the major factors of why a rocket will not work in space is that we also have the idea of free expansion. So basically, with free expansion, what we can see with free expansion, and that is when we have our rocket here, there we go, and we have our pipe work going into the combustion chamber. As soon as the valves are open to allow the fuel and the oxidizer into the combustion chamber, they'll just be sucked straight out by the vacuum of space, like this. And the rocket will just remain stationary. It won't go anywhere. Now, I'm not sure about you, but after watching this video, I mean, how, you know, there's a lot of bullshit in life at the end of the day, and to me, rockets working in space is just part of it.